Welcome back. Today we're talking about the concept of basis. So if I have a vector space called V and a set of vectors called B, then that set is called a basis if it spans V and if it's linearly independent. So we think of a basis, it's a kind of set, as being a minimum spanning set. I could have a larger set that spans V, but B is the smallest possible, or rather a smallest possible set that spans V. We think of each of the vectors in B as contributing something unique to the span. So here's an example of a basis for R2, the set of the vectors 1, 0, and 0, 1. This is actually the canonical example of a basis for R2, because the first vector represents one horizontal unit, and the second vector represents one vertical unit. And this basis actually has a specific name. It's called epsilon sub 2, or the standard basis for R2, also the natural basis for R2. And both of these vectors have names. First vector is sometimes called E1, and the second vector is sometimes called E2. And when we're talking about the standard or natural basis for R2 specifically, we might also call this first vector I hat and the second one j hat. And the reason why this basis is thought of as being so natural is because if I want to reach the point AB in R2, I'm going to travel A many of I hat, or the first vector, and then B many of j hat, the second vector. So let's say I wanted to get to the point 3, 4. Well, I would do that by traveling the vector 3, 4, which would be the same thing as traveling 3 I hat and then 4 j hat. And so we can represent every vector in R2 as a linear combination of I hat and j hat exactly like this. We can also construct a standard basis for R3. So this would be the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. So they just represent traveling one unit, which is why they have the hat symbol over them, one unit along each of these axes. And we name them I hat, j hat, and k hat, or E1, E2, and E3, just like we did for the standard basis for R2. For any Rn, we can construct a standard basis, and it looks like this. So if I want to construct a standard basis for Rn, it's epsilon n, which is equal to this set of n many vectors, E1 to En, where each of these vectors have a 1 in the different component positions and then zeros in all the other positions. So they represent traveling a distance of 1 unit along each of the n many axes that we could imagine in this space. And as a result, if I wanted to get to some point in Rn, say A1, A2, all the way to An, then the way I would get here is by traveling a vector that is the sum of these. Specifically, I would go A1 of E1 and then A2 of E2 all the way to going AN of En, and I would add all of those together, or in other words, I'm traveling a linear combination of the standard basis vectors in order to get to this point, and the number of each standard basis vector that I'm taking in that linear combination is exactly the corresponding coordinate of the point I'm trying to reach. Here's an example of a basis for R2. I'm calling it B, and it consists of the vectors 2, 0, and -1, -1. And we could also name these vectors B1 and B2, and here's what they would look like in R2. So the way that we verify if something is a basis, and we're about to do that here, is we have to verify the two conditions for a basis. Well, a basis is a spanning set of vectors, that is, it spans the space that we're in, which is R2, and it's a linearly independent set. So why don't we verify both of those in order? First, let's verify that, in fact, B spans R2. So if the set B is a basis and therefore spans R2, then I should be able to take some linear combination of its vectors to yield any other vector in R2, xy. So it should be that some C1 times B1 plus some C2 times B2 is equal to xy. Of course, we can rewrite this as a system. This is just the question that we've been asking ourselves throughout all of linear algebra so far. What linear combination of vectors yields another vector? So here's what the system looks like. We can take this to row echelon form by doing 1/2 of row 1 and negative row 2, and then we can take it to reduced row echelon form by doing 1/2 of row 2 and adding that to row 1. So here we have it. We take it to reduced row echelon form, and we find that 1 of C1 is equal to 1/2 x minus 1/2 y, or 1/2 quantity x minus y, and that 1 of C2 is equal to -y. And so for any vector in R2, xy, the scalars that we need to multiply B1 and B2 by in our linear combination in order to create that vector are 1/2 of x minus y and -y. And so, in fact, it does span R2. And here's our proof. We have the formula for the scalars that we need. To verify linear independence, we only need to show that the only linear combination of these vectors that's equal to 0 is when their scalars are equal to 0. Or in other words, the only linear relationship of this kind is the trivial relationship. This creates a linear system that we need to solve. And you'll notice it's a homogeneous linear system, so we can just write it as the coefficient matrix. But this is the exact same coefficient matrix as the one above. We're solving the associated homogeneous system to the one that we had to solve to verify that B spanned R2. So I already know how this reduces. I understand that it goes to reduced row echelon form like this, 1, 0, 0, 1, the one and only solution to this homogeneous system, which therefore makes this non-singular, is that C1 equals 0 and C2 equals 0, or that the trivial relationship is the only one of this kind that exists, and so independence is verified. And that's why I verified span first. So here's another example of a basis. I'm not going to verify it, but I hope it's pretty obvious and that the last example showed you what the process is like. We just verify span and linear independence. But here, consider this matrix, okay? So this is a homogeneous matrix, and when I take it to reduced row echelon form, it looks like this. So obviously I have my main diagonal of 1s right here, and then I have 0s below and above the main diagonal. But because this is a non-square matrix, I necessarily have some other kinds of entries to the right of that. And this is a system of equations with 4 variables. So we have x, y, z, and w. If I have 2 equations and 4 unknowns, I'm placing less constraints on my variables than I have variables to account for. So my unknowns are free to vary. If I had 4 equations for 4 unknowns, then that would be enough equations to specify 1 point in space, in R4 in this case, or in other words, 1 unique solution. But since I only have 2 equations, I can only narrow down my choice of points or combinations for x, y, z, and w that satisfies these 2 equations in the system to, at most, a plane. And so the solution set looks like this. You'll notice it is in fact a plane because it's parameterized by the free variables z and w, which multiply these 2 vectors. And so we can think of these 2 vectors as basis vectors for this subspace, which is a plane in R4, and these 2 red vectors would be the vectors that z and w multiply. And finally, just one more example, we have the trivial space. The trivial space has one and only one basis, and that is the empty set. And this should be reinforced by the fact that I mentioned in the previous video, which is that the empty set is the one and only linearly independent subset of the trivial set. You might be wondering to yourself why we're even interested in these so-called minimum spanning sets, these bases. Well, the reason why is because if I have a vector space V and a basis B, every vector in V can be represented as a linear combination of the basis vectors, and it can be represented as only one linear combination. If I find the linear combination of the basis vectors that equals a certain V within this space, then that's the only way I can combine the basis vectors to give V. Here's why. So let's say I have 2 different ways to represent V. First is that V is equal to C1 times B1 plus all the way to Cn times Bn, where B1 to Bn are just the vectors in V. Okay, and then the second way I represent it is with different scale, d1 times b1, dn times bn. Well, if this is true, certainly we know that V is equal to itself, so why don't we equate both of these ways to express V? C1 times b1 to Cn times bn is equal to d1 times b1 to dn times bn. Well, what if I subtract everything on the right? I subtract my second way of representing V as a linear combination of the basis vectors. Well, then I would get the following. I would combine my coefficients for each respective basis vector, so I would get that C1 minus D1 times B1 plus C2 minus D2 times B2 all the way to Cn minus Dn times Bn equals what is left on the right side, which is the 0 vector. So I find that this combination of these vectors is equal to the 0 vector. But since B is a basis, all of these vectors make a linearly independent set. Therefore, the only way that I can have this combination of vectors is equal to 0 is if all of their scalars are equal to 0 themselves. And if each of these C1 minus D1, C2 minus D2, generally Ci minus Di is equal to 0, that implies that Ci equals Di. So all of these scalars are actually the same. Therefore, all representations of V using B are the same.